Good morning, and thank you for joining us. I'm Ann Motrunich, a writer in Caltech's Office of Strategic Communications. Welcome to Conversations on the Quantum World. This series is hosted by the Caltech Science Exchange and designed to give all of us a chance to hear directly from Caltech researchers who are advancing quantum science and harnessing it for future technologies. We are joined today by Nai-Chang Yeh, Caltech's Thomas W. Hogan Professor of Physics. Dr. Yeh's research centers on quantum materials. She engineers, measures, and creates these materials at the nanoscale. Dr. Yeh has co-directed Caltech's Kavli Nanoscience Institute and is especially interested in the unusual things that electrons and light do in these materials. Professor Yeh, thank you for joining us.
Pleased to be here.
Yeah. Let's dive right in and do some scene setting. Can you tell me, when engineers and physicists make new materials in electronics, what kinds of sizes are they now working with? How does that look?
Typically, the sizes that people are working with these days are mostly at the nanoscale or nanometer scale, which is a few billionths of a meter, a scale that's related to the size of molecules or a few tens of atoms. To work at this length scale, special tools are needed because they're so tiny. You will need to use special tools to image the tiny structures or even to fabricate devices at such scales. And some of the tools that you can use include like electron beam microscopy, lithography, focused ion beam microscopy, lithography, and also there are other things like scanning tunneling microscopy, atomic force microscopy, nano scanning optical microscopy. And given these, the tiny sizes of these things, they're even smaller than typical dust particles. And so that's why people will have to often do these observation and fabrication in clean room environment.
Mm-hmm. It sounds like kind of a wonderland of machines and equipment. You've told me before that at those scales, everything's quantum. What do you mean by that?
Basically, the mere existence of materials is based on quantum mechanical principles. Because at atomic and nanoscales, where quantum mechanics, actually quantum physics takes over from classical physics. And so, for instance, light and electrons, they actually would exhibit quantum phenomena such as particle wave duality, and they also obey the uncertainty principle. And so, for instance, we would describe the behavior of electrons in materials instead of like rigid particles. We would describe them in terms of wave-like probabilistic distributions, and these are known as wave functions. And so, so materials are actually held together because electrons distribute like wave functions, holding structures together. And so that's completely quantum mechanical. And also, another example, you can place an atomically sharp tip very, very close to a sample surface, a conducting or semiconducting material surface. And if you place it very close, but with a vacuum gap only like on a nanometer scale or even smaller, then electrons actually can tunnel between the sharp tip and the underlying sample, which is again quantum mechanical. It cannot happen in classical physics. And this is actually the principle of scanning tunneling microscopy, for you to image and to manipulate things down to atomic scale. On the other hand, for photons, for light, you actually don't think of them as waves in the quantum mechanical scale now. You think of them as photons. Photons are actually quantized units of electromagnetic energies. And so, so they can interact with materials, and materials can absorb photons or emit photons. So these are also quantum mechanical, and these concepts actually are essentially are essential to a lot of light-related applications of devices, etc. these days.
So things that we take for granted at the scales where we live things that seem continuous to us are discrete and jumpy at this quantum scale.
Yes.
Mm-hmm. And now, if when we get down to those scales, everything is quantum, what is meant by the term quantum materials? If every material is quantum, then how do quantum materials, how is that different? Does it depend who you ask?
Okay, so quantum materials give you a little historical background. It was a phrase originally invented by researchers in condensed matter physics. They refer to materials, particularly called strongly correlated materials, which are related to, it's an umbrella term referring to materials that, that actually have properties that cannot be easily described by semi-classical approach or the low-level quantum physics. But nowadays, people actually generalize quantum materials to other things, including topological materials, low-dimensional materials, and engineered quantum materials. So for instance, strongly correlated materials, let me try to explain a little bit. Please bear with me because these are a little bit of jargons, but let me try to explain them more simply. Strongly correlated materials include something you are probably familiar with, high temperature superconductors. These materials, their electronic properties are actually interdependent. So unlike simple materials like noble metals or typical semiconductors, strongly correlated materials cannot simply be understood by looking at one property or just approximate the rest. The electronic charge, spin, and orbital degrees of freedom, as well as the background ionic motions are all interdependent. So these are called strongly correlated materials. They're kind of hard to deal with. You have to create new theory to understand them. And then the topological materials refer to materials that have properties that are invariant under topological deformation. And these materials exhibit very interesting properties on the surface that actually reflect what they are in the bulk. But these properties can be very well preserved, not sensitive to imperfections. And so they can be useful for various things. Low-dimensional materials refer to materials that can exist in dimensions smaller than 3 dimensions. So such as in 2 dimensions, like graphene, you probably have heard of 2-dimensional sheets, or 1-dimensional nanowires, or such as carbon nanowires, or 0-dimensional dots, like quantum dots. They're related to semiconducting nanocrystals. So these are low-dimensional materials usually because of quantum confinement. So they always exhibit very interesting quantum properties. And then you can start combining them together to create heterostructures and have even more interesting properties. Then another class of materials are called engineered quantum materials. For instance, you can use a laser to cool atoms or ions and arrange them into a few tens or hundreds of them into some special structures that you desire. Or you can use nanofabrication techniques and make things down to very, very small scale, which can create new properties and that originally may not exist in the original materials. So these are called nano engineered or engineered quantum materials. And so, but often we can combine different techniques, or we can grow materials also down to an atomic layer, one atomic layer at a time. So the definition of quantum materials these days are much broader than what it was originally created.
Mm-hmm. I want to go back on a couple of those things and just ask a couple of clarifying questions. Mm-hmm. One is, for someone like me, when you say that these topological materials in that kind of middle category are invariant under deformation, does that mean if you reshape them, they stay the same in their properties?
Okay, this reshaping, if you want to describe it literally, that's one way of visualizing it. But the reality in real material system is that if you think about electronic wave functions, and so if you run into impurities, it's like there is some deformation. And then because you have some special topological properties that are non-trivial, so those properties will not vanish when they encounter imperfection and being deflected. That's probably the way I would describe it. Yeah.
Okay. And then going way back to the beginning of your answer, there was one thing I wanted to touch on because I've read about it in other places. You said they can't be described using, I think you said they can't be described using semi-classical approaches. And if you could just explain for some of us the sense of like what classical, semi-classical, and quantum are, I think that would be helpful.
Okay, semi-classical, so this is a little technical, but let me try to explain it a little more simply. So if you have, so this is so-called single particle approach. So if you have a many body system, so in materials, we have many atoms. It's about 10 to the power of 20 to 23rd. It's an enormous number of particles. But the semi-classical approach is such that you try to describe the electronic properties, how electron moves around, behaves, and then you can sort of average all of the background into some effective property, and then you describe how your one electron move around in this effective background. But in strongly correlated systems, then it's not so easy to do it that way because it's not going to be quite accurate. Yeah.
Great, thank you so much. Are we already using quantum materials? Are there any in my phone, for example?
Oh yeah, absolutely, tons of applications already. But before I describe the examples of applications that quantum materials have been used, I need to emphasize an important point. That is, quantum materials are not only useful for quantum technology. Okay, they can be used for everyday things. And so let me take the first example, which is a low-dimensional system and also a strongly correlated system. That is, typical semiconductors are not classified as quantum materials, but you can take two pieces of semiconductors and make them into thin films and light them on top of each other. Then you create an interface. When you do it right, what you can do is you can create a sheet of two-dimensional electrons, and these two-dimensional electrons are strongly confined. Now, if you apply a strong magnetic field vertical to the planes, then they actually turn to a very strong magnetic field that's vertical to the plane. And then you create very strong electron confinements and by the magnetic fields, and then they will create quantized steps of transverse resistance. And such resistance are so precise, the resistance values are so precise that they are now being used by National Institute of Standards and Technology as resistance standards to 1 part in a billion, 1 part in a billion kind of accuracy. So this is good for metrology, for instance, strongly correlated systems, low-dimensional systems. And there are other low-dimensional systems that are already being used, like graphene. Graphene is also already used for a lot of things, like such as in energy storage, additive manufacturing, surface passivation, electronics, textile and printing technology, and a whole bunch of things. And also another low-dimensional systems would be like quantum dots. They're in semiconducting nanocrystals, can be used for light-emitting diodes, photovoltaics, high-definition television and display, photodetectors, photoconductors, biomedical and environmental applications, single electron transistors, many of applications, and also strongly correlated systems like high temperature superconductors are already being used. For instance, they're used in scientific magnets already at National High Field Magnet Lab in Tallahassee, and also they are used for power cables, transformers, although in a smaller scale, and also motors and fault current limiters, and also filters, and being used in nuclear magnetic resonance and magnetic resonant imaging technologies. And then, of course, as we shrink all of our transistors down to smaller size transistors and devices, they are naturally entering into the quantum regime. And so there's quantum confinement effect, and those systems can also be classified as quantum materials. So you can see they're being used already.
That's a lot more use than I realized, actually. That's a lot. Huh. And, you know, I think you and I in conversation a while ago over tea, we were talking and you said the future is just inextricably linked with these materials. And I thought that was so interesting because they seem very exotic to me. Clearly, they are not as exotic as I thought they were, if they're already in so much. But can you tell me, what are these materials better at? Why do we want them? And why are they so important to the future?
Well, because right now, for instance, one of the major challenges in advancing semiconducting technology is that we need to continuously decrease the size of the nanoelectronic components and devices. And then that leads to new challenges in the quantum limit. For instance, we have issues related to quantum conductance, quantum capacitance, quantum fluctuations, as well as increasing heat dissipation and many materials issues associated with shrinking the dimensions. Now, if we incorporate quantum materials, we can actually introduce additional electrical and thermal conduction channels and providing protection barriers and layers to prevent atomic migration in nano devices and nanostructures and interconnects. And also these materials, they have interesting properties. You can combine with, you can do proper design to develop additional functionalities. And so through clever designs and heterostructures or interlayer properties. And so all of these can lead to potentially higher densities of smarter devices with better operation efficiency, speed, faster speed, and lower energy consumption for smaller and smaller volumes. And so that's becoming an important challenge for at least for the nanoelectronic applications. And of course, there are many other areas, as I mentioned earlier, they are already being used in applications because they have very special properties. And so one can design and manipulate things down to nanoscale to achieve things on demand, achieve properties on demand.
So it sounds to me as if quantum is both, forgive the metaphor, but the bad guy and the good guy in this scenario. That, like, as you shrink these technologies, you run into these quantum effects that are super perplexing and hard to deal with, atoms migrating where you don't want them, things happening. And the best way to solve those problems is actually to introduce controlled quantum effects. Is that a fair?
Yeah. So once you know what's going on at the quantum scale, then you know how to overcome issues or take advantage of special properties at the quantum scale.
Mm-hmm. Yeah. I think people will want to know about the link between quantum materials and quantum computers, and they are interdependent, are they not?
Kind of. Okay, so let me elaborate. And so currently, the most scalable, I mean, as you know, to make quantum computers, you need to start with qubits that are quantum bits. And currently, and of course, not just quantum bits, and you need to have quantum memories, quantum network, quantum transducers, all of those things. But the most essential part is the quantum bits, and the quantum bits right now, the qubits, or so called, currently they're made out of mostly the most advanced quantum bits are made out of superconductors, but they are low temperature, very low temperature superconductors. And so there are many issues with that. And those, we won't necessarily call them quantum materials. They're kind of well-known superconductors, but but there are many materials related issues, and they only operate at very, very low temperatures. So that makes these qubits not very scalable. And so, of course, as I mentioned, that some of these very interesting high temperature superconductors, for instance, there are quantum materials. And therefore, if we can advance interesting and good properties of higher temperature superconductors, then it can certainly help the development of qubits. But also currently, though, there are qubits already made out of quantum materials, such as people use quantum dots as the qubits, or they use cold atoms as qubits. So these are the real quantum materials are already being used as qubits, and of course qubits are directly related to quantum computation. But typical quantum dots and cold atoms, so far they are not as well developed as the superconducting qubits right now. But that's the area that can have impact on quantum computation. But of course, there are other quantum materials-based devices that can actually help things like quantum memories, quantum transducers, and that will be quantum transducers will be like you can switch between electronic signals and photonic signals. So if you develop computations in the lower local scale, you want to transfer signals, you want to have photonic signals, and so all of these are going to be can truly benefit from the advances of quantum materials. So I would say that that's probably the most direct relation between quantum materials and quantum computation.
Well, thank you. We've talked a lot about applications already, but are there any other applications you wanted to mention, future ones, any you're particularly excited about?
Oh, there are many potentially interesting things. For instance, we just mentioned about quantum. So it's quantum information technology, better qubits and also better quantum memories, and with scalability. And also for typical information and communication technologies, quantum materials can make impact. And of course, for nanoelectronics, nanophotonics, nano-optoelectronics, nanolasers, these are definitely useful for sensing, for detection, and as devices being used in a broad range of like Internet of Things and in consumer products. And also you can develop wearable, flexible electronics, also for consumer products, but also for biomedical applications. And then, of course, a lot of these quantum materials also have special properties for energy conversion. They can be used in solar cells or in fuel cells. And also they can be used for energy storage, in batteries, in supercapacitors, and also for sustainability generally, like for filtering, desalination. And of course, you can also make lighter and stronger structural materials. And you can also use them for like navigation, astronomy, metrology, many things that can all benefit from studies of quantum materials.
Wonderful, thank you. I understand that this is one area where defects can actually be a good thing. When you have a flaw in a perfectly ordered quantum material, it can open up some opportunities. Could you tell about that?
Yeah, actually, it's like the world is not perfect, and sometimes we can take advantage of imperfection. So there are things called defect engineering, for instance. So you're going to go down to quantum scale, and you can actually manipulate and create defects on demand, for instance. And this way, you can actually implement some desirable properties. For instance, there are already examples. So you can have atomic scale defects that there and some nanoscale strained properties in certain two-dimensional materials, and they can become quantum emitters from these sites of strained or create defects that you created. So they can be really very, very precise quantum emitters, and they can be used for quantum information processing, for instance. And also vacancies in diamond and silicon have also been used as, they can be as color centers and also for sensitive detectors. So there are plenty of examples to utilize defect engineering.
Is a quantum emitter like, I'm sorry, but is it like a laser? Or what is that?
A quantum emitter is like a little light emitting atom.
Okay.
Very, very localized and only limited number of photons coming out of it. But it's sometimes you want to have good control. You don't want to have billions of photons all come out together. You cannot control them. So these quantum emitters, you can truly position the emitting site and the amount of photons that come out of them.
Mm-hmm. And in diamond, you can do that with a hole in the diamond that produces color.
Okay, there are color centers. That's because, okay, this gets a little technical. Diamond itself is known as a wide bandgap semiconductor. So you have a very, very wide energy bandgap. And so many, light with all many range of energies can pass through this energy gap. But if you have some impurities, then the energy scale is much smaller. And so when you try to shine a white light through it, some of the light can be absorbed instead of going out as transparent, because usually a pure diamond is completely white, right? White colored. Transparent. And so that means light is not absorbed. But if you have impurities, vacancies, then at those sites, light actually can get absorbed and then re-emitted for certain frequencies. And so you start seeing colors. So it depends on which color gets absorbed, and that's what you have. Mm-hmm. So that they are called color centers. Sorry, some technical jargons, but that was a good question.
Oh, well, thank you. I really appreciate you working with me on this. One more really general question, and that's just a quick vision for how the future would look different if we can really turn the physics to our advantage here.
Oh yeah, I think it will be a brave new world with lots of good things. So I would say that it can become a new quantum era with scalable quantum computers and quantum networks. And of course, you can do fast computations and many things become possible for technology. And then you can have better, faster, smarter, and smaller electronics, photonics, sensors, devices, and instruments based on quantum materials. And so you can use them for scientific exploration. You can use them for aerospace expedition. You can use them in consumer products, medicine, or even national security. And also you can have more efficient energies and also larger energy storage capabilities for a greener environment. So there are many potential good things related to everyday life, research, and sustainability.
Nice. I'd like to ask you two personal questions, if I may, and then we'll just wrap up with one other question before Q&A. But the personal questions, one is about your advisor. You studied under the legendary Mildred Dresselhaus, who, a leader in nanotechnology, in carbon science, in electronics, and a leader in science itself. What do you think was the most valuable thing you learned from her?
I actually learned a number of very good things, but just in case, I'm not sure if the audience know Mildred Dresselhaus very much. So let me just briefly mention that she was actually the first woman professor in electrical engineering and physics at MIT, and also the first institute professor at MIT. And she has won all kinds of honors, including National Medal of Science, the Buckley Prize for Condensed Matter Physics, Kavli Prize for Nanoscience, and also presidential Medal of Freedom from, she was awarded that from President Obama. And she was also the director of DOE basic science for some time. So she had made enormous contributions to the world. And so what I learned from her really is that she is always very dedicated to everything she did. And she was passionate about research. And most of all, she was incredibly kind and generous to people. And I would say that she has achieved the pinnacle of great scholarship. And so in our Chinese culture, usually we regard the pinnacle of scholarship as the best accomplishment of a person, actually. And there are three important ingredients associated with it, in my opinion. That is virtuosity, and then versatility, and virtue. So Millie, of course, Mildred Dresselhaus has accomplished virtuosity in her career, but she was also very versatile in many things. In particularly, she was actually a fine amateur musician. She played the violin and viola. And then virtue, that's something that usually doesn't exist in Western culture for great scholarship. But I mean, for great scholarship, you don't worry about virtue, but actually in Eastern culture, we actually consider that highly. And there's no doubt in my mind that Millie was highly virtuous. And so yeah, these were very, very good attributes of her. And so yeah, I learned from her. She was a great role model to all of us who interacted with her, whether they're her students or not. People were always impressed by her.
Yeah. How did you come to her? How did you become part of this field? And what keeps you coming back every day?
Actually, so I was lucky. I was just a student who didn't know anything about anything from Taiwan to MIT. That was my first international trip. And I didn't even know which professor I was going to work with, because that was before the internet time. I couldn't find all of the information about all professors. Millie reached out to me. She invited me to be her student. So I was extremely lucky that way. But I love the field. So I think I got lucky. I picked the right field that I have been enjoying since. So I would say that study of quantum materials actually involve exploring and manipulating the quantum nature of many body systems. But you do that in realistic materials. So realistic physical systems. And so it is fascinating, challenging, and also satisfying for me. And I feel that the fact that I can enjoy learning new science from studying quantum materials, but also design and create new properties in these systems is something that keeps me going. So basically, it's the fun of science and the relevance to technology that drives me. And also, I consider, for this reason, the field of quantum materials is truly exciting.
Well, thank you. I have been taking up all your attention, and we actually have a bunch of questions from audience members. So let me switch over to those. First off, from Alexis, if you want to be an investor, what should you watch out for when you're pitched a business based on quantum materials?
As an investor, okay, so I think as an investor, one should at least make sure that you have proper technical consultation, so you're not just blinded by the fancy things that are being said. If you have very good technical people to consult with, then you will know whether things that are projected are feasible and can be accomplished within reasonable time frame. There are lots and lots of interesting properties and opportunities, but not all of them can be easily achievable within reasonable amount of time. And so that's something that having people to talk to who have truly solid technical background will be important.
From Ahmed, will quantum materials ultimately replace all the old technology?
I'm sorry, replace all
the old technology.
Old technology.
How transformative are we talking?
It can be very transformative, but I would say that the best world is that older technologies and these new technologies can coexist, because it depends on what you're working on. So for instance, I was talking about these quantum materials, for instance, graphene, carbon nanotubes, they can be used for lighter and stronger structural materials, and then you can use them for certain things. But it doesn't mean that everything can be based on those. For instance, sometimes you still need steel beams, you still need some solid concrete. Depends on what applications we are talking about. But of course, when you shrink things down to small scale, if we really talk about on-chip applications, or if you want to do aerospace expedition or something, you want to have lots and lots of smart devices in a small volume, then I think quantum materials really are the way to go, because you're dealing with quantum science down to those length scales. And so it depends on the applications. I won't throw out old technologies yet.
Nice. I have a question here about bio-inspired approaches. Kevin asks, have you seen your peers begin to consider quantum biological processes like photosynthesis as a resource of ideas for developing technologies?
Yes, absolutely. Actually, people are working on such things. And actually, I myself have a little bit of involvement in using quantum materials for potential bio applications. Recently, we have published a paper that basically we are able to use graphene to protect thin layer of gold that are typically used in wearable bio devices, biomedical devices. And so you can use graphene to protect them, so that and to enhance the flexibility. So but that's the area of medicine. But yes, photosynthesis, etc. People are working on it. People are considering how to enhance the efficiency of, say, photosynthesis is one area of energy conversion. Yes, so at Caltech, actually, there are people working on it.
Yeah. And then we have a couple questions about getting into this area and encouraging people to get into this area. I think I'm going to encapsulate them in a question from Akanksha, which is, as a teacher, how could a person help students be attracted to quantum physics from an early age? How should a beginner start studying quantum mechanics?
Okay, beginner, how do beginners start? Well, I think I think usually people were first fascinated by the potential of benefits that you can gain, and I think that's one way that people realize. For instance, these days, young people realize that sustainability is a critically important issue, for instance. And then you can see that a lot of these quantum materials potentially can address some of these issues. So from the potential for making the world better, that will be one way of bringing young people, young talents into this kind of research. But sometimes it's just the mere beauty of science. Actually, I was drawn to physics. I didn't even think about applications. I just love it. And so I think, but quantum science is a little more advanced for young people, for children, for instance. So people need to build up some knowledge in order to truly appreciate quantum science. So I think it will be the best just initially show people all the wonderful things that quantum science can do. And then from there, then maybe people can dig in, young people, students can dig in, and then they started developing appreciation for it. I don't have the best recipe for it, but because I was just drawn to the beauty of science, but not everybody will be motivated by that. People may want to know, what can I do with it? If I can make the world, make my future better. So that would be another motivation. But as I said, you know, this field has beautiful science and at the same time, highly technologically relevant. So people can be drawn to it either way, I guess.
Mm-hmm. From Nilo, how are devices that rely on quantum materials made resistant to damaging quantum processes, like even radiation?
I'm sorry, could you repeat the question one more time?
Sure. Yeah. If we have devices that rely on quantum materials, how are they made resistant or proofed against damaging quantum processes? Radiation was one example given.
How would they resist processes that may damage the?
I wonder if that means, like, when you get down to this scale, how do you emphasize the good quantum processes and avoid the bad ones? We got into that a little bit earlier.
Well, okay, again, how would you, so there were things like, for instance, if you have topological materials, certain processes actually are not going to be devastating to them. But I'm not quite sure how to address this in simple terms, because it depends on the situation that you're dealing with. You can develop things, for instance, you can go to lower temperatures, that's one way, or you can add protection layers or something to prevent external unnecessary photon interferences, for instance. So it really depends on the specific systems that one is working on. But in general, if you understand the properties that you care the most about, then there should be, you can try to work out a way of preserving the specific properties that you want to work with, and try to use other things to eliminate the interferences. So I'm not sure if I, because this question is a little too general. I don't know how to really address it more precisely. To me, I have to look at what I'm working on and then think about what kind of solution I'm going to provide, I'm going to come up with. Yeah.
So it's really contextual to the specific problem.
Right, depends on what you're working on. Yeah, depends on exactly which processes you care about, what materials you're working on.
I have one question from Victoria here. Do topological quantum materials have advantages in using them for quantum computers? What do you think?
In principle, yes, because they're more fault tolerant, and so you can preserve quantum coherence much better. On the other hand, it's like a double-edged sword. When you have something that's insensitive or less sensitive to external perturbation, that also means it's much harder for you to manipulate it. And so if you want to use them, if you want to do entanglement, you want to transfer signals, yeah, the coherent part is very well preserved. But if you want to do other things, it may be more difficult. But in general, yes, topological quantum computation will be a very exciting direction to go if we can find the right kind of systems to provide it. People were actually working hard trying to use something called anyons that they are related to what I mentioned earlier, two-dimensional electrons. You apply very strong magnetic fields and you turn electrons into a new state of matter called anyons. And supposedly they have very, very interesting topological properties. But the problem is that it's very hard to control. And so people, I think, spend more than a decade exploring it. And I think the progress is limited. So right now, the best qubits right now are still this good old low temperature superconductors making into squeezed superconducting quantum interference devices and Josephson junctions. People are using those right now just because of the difficulties of control.
Yeah, sometimes like neural nets, the ideas are so far ahead of their time that you have to wait for everything to catch up.
Right.
I think we are out of time for questions, and I'm so glad that you had time to answer so many of them. Thank you so much, Dr. Yeh, and thank you to everyone for joining us today. In the next conversation on the quantum world, you can find out why space might not be what you think it is. Registration will open soon for that event, which is July 12th. My colleague Whitney Clavin will interview physicists Catherine Zurich and Rana Adhikari about quantum gravity. In the meantime, I hope that you will explore the Caltech Science Exchange online. It is at scienceexchange.caltech.edu. You can find clear, trustworthy explanations focused on really important areas of science and technology, areas where there might be a little hype or misinformation or just confusion, areas that are in the news. It's very helpful. Beyond the really helpful quantum explainers, there are sections on COVID-19, earthquakes, voting and elections, very topical, and sustainability, also topical. Thank you again for coming today.
Thank you, everyone. Thank you, Anne. Bye.